invitation. Thanks everyone for coming. I'm going to talk about like a range of things that connects to projects I've been working on with my collaborator Sean Gribb for quite a few years. I think some of them, certainly some of you may have seen before, probably most of them, but probably not in this order. And then I'll also talk about a few newer things that kind of just came to me in the last few weeks, really. So the kind of theme is really a particular problem in motivating an approach to time in quantum cosmology, which really relates to the understanding of constants. But we're going to kind of see lots of different ways of approaching it as we go. And I just thought it would be useful just to get a kind of high-level view of the type of approaches that I'm kind of setting against each other. And seeing as we're in the LSE, I just had to call them research programs. And so, on the one hand, we can think of a much better known, and this list of references could be extended to probably hundreds, research program that really follows an approach to quantization of gauge theories in general, but in particular theories with a gauge symmetry or a symmetry, which some people call a gauge symmetry, called time reparameterization invariance. Particularly, we'll be talking a bit about toy models of cosmology. We don't have a full theory of quantum gravity, but people have studied toy models of quantum cosmology all the way back to DeWitt in 1967, and more recently in the context of loop quantum cosmology, Bojewald, and which I'm sorry I can't pronounce, Bojewald, I think it's actually supposed to be, and Ashtekar. And they have these famous singularity resolution results for these toy models. And this program which really follows on Dirac's approach to quantization, worked on by many others as well, that's kind of framed in this really good textbook by Henno and Teitelboim. And people often call this the timeless approach. I think that's wrong, to be honest. I think it's really a kind of relational time approach, or it can be understood in terms of a relational time approach. And particularly Carlo Rovelli and then later Bianca Dietrich have shown we don't have to completely abandon time in this approach, but I think there's aspects of time that we do lose. And so this is a kind of mainstream research program. It leads to an equation which is like a time-independent Schrödinger equation, and we recover time in some kind of limit internally within that, and that's called the Wheeler-DeWitt equation, which was first written down by DeWitt. And I'll talk about a specific toy model version of that in quantum cosmology later, or at least it will feature later. The alternative research program, and I kind of, mea culpa, I think I haven't always recognized the extent to which there was earlier work doing very similar stuff to the stuff that me and Sean did, and I'm very happy to do that now. The alternative research program really kind of is motivated to some extent by a different way of thinking about time reparameterization invariance as a symmetry. The kind of earliest versions of this we actually find, and I'll talk about a little bit, in a treatment of the relativistic particle by Fock and Stuckelberg, way back in the late 30s, early 40s. More recently, Carlini and Greenside, which are papers I really want to study more in, and haven't studied in enough detail, kind of extended this approach and this alternative way of thinking about quantization, and particularly made reference to the idea that this involves thinking about constants of nature, particularly the cosmological constant, differently. And there's a really nice review article that kind of summarizes those results, the earlier Stuckelberg results, and then also relates them to work that I did about 10 years ago with Sean Gribb, and that Bill Unruh and Bob Wald and some other people more recently have done on a particular approach to cosmology called unimodular gravity. And to some extent, these are all different ways of presenting essentially the same idea, which is that, at least in the cosmological context, you reinterpret the cosmological constant as a constant of motion rather than a constant of nature, and that allows you to take superpositions of it with the quantum theory, which gives you a model which looks structurally very similar to a time-dependent Schrödinger equation. So there's lots of challenges. I've been talking about this stuff for, like I said, more than 10 years. People often make objections. one objection, I guess, that not many people have made, because I haven't given a talk like this very often, which is what I'm going to focus on first, is, well, why are we reinterpreting constants this way? What's your philosophy of constants? Why do you think that constants are the types of things that one reinterprets? And so I'm going to talk initially a little bit about this kind of idea of relating the way we interpret a constant as a constant of nature or a constant of motion to a particular question in epistemology, or a particular way of thinking about kind of, given an underdetermination of what we know, what choices we can make or what choices we can change. And this idea really goes back to Poincaré. I'll talk a bit about that, and I'll relate it to some other ideas related to superselection rules. Another challenge, which is the one I'm kind of quite happy to deal with, because I wrote a whole book about it, is like mathematically what's going on if this time of parameterization invariance is a gauge symmetry, and that gauge symmetry leads to this particular time-independent Schrödinger equation, the Wheeler-DeWitt equation. How can you say that you've kind of relaxed the constraint, you've moved to a time-dependent version of it, so you're no longer imposing it to kind of superselect to one zero eigenvalue, and you're still implementing the symmetry. And the response really is that it's not a gauge symmetry once we're very careful about language. Third one, kind of going back to the Lacantoshian idea, given that there's no real empirical evidence about quantum cosmology, and because of the way things are set up, the kind of Dirac-DeWitt case is just a special case of the alternative case. There's an undetermination problem, because we clearly can't say that the alternative is inconsistent, because it's actually a special model of our models. So is there any reason to think that this alternative program is more progressive or progressive at all? And I'll answer that by reference to some work that Sean and I did some time ago, and some more recent work by Stefan Gillen and collaborator looking at singularity resolution. To some kind of idea that there's some formal problems, at least, that the alternative program is kind of making progress on solving. And the fourth challenge I'm just putting up here, because someone's probably going to say this anyway, how on earth is this going to work for inhomogeneous cosmologies? I'll say a little bit right at the end, if I have time, about how we haven't solved this problem, it's what we're working on at the moment. So, I mean, rather pretentiously, I just came up with a name. I'm going to call the principle that I'm going to use that's epistemological, relate to interpretation of constants, the new Copernican principle. If you've got a slightly less pretentious name, then let me know. Useful. And so really the principle, Sean, I think, in fact, found in Poincaré, in a kind of much read and pored over by philosophers book, and it's even in the most famous passage, but it doesn't seem to have been really discussed very much in Science and Hypothesis. And those of you who know it well, you should all know it well. There's a particular part where he talks about imagining a solar system that's occluded by cloud, and the role of the integration constant related to angular momentum for astronomers who don't have access to the rest of the solar system in making predictions. And it's usually, obviously this is in the context of Newton's bucket experiment and Thébault relationism. But there's also kind of another part to that passage where he just says these kind of really interesting, slightly elliptic remarks about the interpretation of constants. And it runs as follows. When observation shows us that a certain quantity is constant, then two perspectives are open to us. Either there is a law that says this quantity cannot vary, and it's by chance that at the beginning of time it happened to take one value rather than another. Or there is a law of nature imposing on this quantity one value rather than another. As long as nature has secrets, this distinction will always be highly arbitrary and precarious. And so the idea is that so long as we don't know everything, the distinction between which constants are constants of motion, which constants are constants of nature, is kind of underdetermined. And in one way of thinking about this is in the solar system case, what's the thing that we know that this should be not understood as a constant of nature for the solar system, is that we can see all these other solar systems. And we realize it's a kind of contingent fact. We can kind of see the modal kind of structure that's inherent in the idea that our solar system could have had a different angular momentum. Whereas other constants, we don't have access to other regimes in which we can see them taking on different values, and so we don't have that kind of inference available to us. And I mean, amazingly, this passage and the implication for constants, to my knowledge, has only really received one detailed philosophical introspection. Again, if people have references to me, please let me know. It's in Schlick. So Schlick, in his collected papers, he has a 3 or 4 page discussion of this, and it's very interesting. I've got more to say about what Schlick said, but I'm going to skip that. To my knowledge, no one else has really latched onto this point, or at least latched onto this point in Poincaré. Someone who's talked about a very closely related idea, without reference to Poincaré, is Lévy-Leblond. And so this is in a paper from 1977. It's a really wonderful paper. And he does what's very useful. He classifies constants into 3 different types. Type A, physical properties of particular objects, for instance, masses of fundamental particles. Type B, constants characterizing whole classes of phenomena. He talks about coupling constants. I would also think about constants that appear in Lagrangians or Hamiltonians of particular theories. And then type C, universal constants, things like C and H bar that apply to kind of most general theoretical framework that we have. And he says, I think very interestingly, that not only does a type fundamental constants, or its absence thereof, depend on the history of physics, but it may also vary according to one's implicit epistemological position. So the idea is that we can think about certain constants, not just as being constant of nature or constant of motion, depending upon what we know, but also being constants of nature of these different types. And our kind of, our epistemology, what we know, seems to be related to how we think about the status of constants. Now, a lot of this is very interesting philosophically and perhaps metaphysically, but in practice, at least in classical theory, it's not clear how much hangs on whether a constant is a constant of nature or a constant of motion. In particular, the way that classical theories work, ultimately it's going to be empirically equivalent to reinterpret a constant as a constant of nature or a constant of motion. You're really changing the understanding of the modality of modality in the theory, but you're not changing the theory's predictions. But in quantum theory, that's not true. In particular, usually what we think of as constants of nature, we'd associate with superselection rules. Formally, a superselection rule, I think, again, one of the very few discussions of this in detail, Brian also has some stuff on it that's really nice, is by John Earman. And he thinks about, he talks about superselection rules, which he gives the standard definition of superselection rule, as a statement we're able to decompose the full Hilbert space into subspaces that no observable has non-zero matrix element in both spaces. And we could then think about superselection rules for each of the kind of Lévy-Leblond type of constants. In particular, for the type A constant, we get what we standardly associate with superselection rules, for example, for mass and charge. And these are what French and Redhead and other people have called state-independent properties. And so we get the idea that you can't have, for example, superpositions of mass eigenvalues, which matches with the Earman definition and also matches with the idea that mass is a state-independent property, unlike angular momentum. And so there's a nice formal argument that you can give to motivate these type A superselection rules coming from symmetry. In particular, you can use in kind of non-relativistic quantum mechanics, you can use the structure of the Galilei group to motivate mass superselection. And there's also an argument from SO3 to charge superselection. However, this is a really interesting move that Giolini pointed to, and I'm sure others have explored earlier, where you can actually kind of play a game where you reinterpret the variables, expand the symmetry group, and particularly for the Galilei group, you move from Galilei group to its central extension, which is the Bargmann group, which doesn't have different empirical consequences but has a different structure. And this allows you to potentially lift the superselection. And he has a parallel argument for spin. And so if we want to try and understand how does what I just said relate to what about superselection rules, relate to what I said earlier about epistemology, I think here's one, the natural thing to do is invoke decoherence. So we do find superselection rules which aren't kind of gnomic in the sense that they impose kinematical restrictions. They're dynamic. They're coming from some particular contingent process that has allowed us to kind of trace out certain degrees of freedom, which is obviously related, with some fundamental sense related to what we can know, or less what we, maybe not in that, if I make it less agential, what degrees of freedom we have manipulable access to. But it's still epistemological in that kind of objective sense of any representation from a particular perspective that only has access to certain degrees of freedom will be kind of forced into accepting this as a superselection rule. But that doesn't mean that if we give that enrich that representation with more access to more degrees of freedom, the superselection rule will still necessarily hold. And I think this is how I'd understand superselection rules for molecular chirality, as Alex Franklin and Vanessa Seifer talk about in their really nice paper. And what Giolini says is that we should think about these as soft superselection rules rather than hard superselection rules. They kind of emerge dynamically in a kind of specific circumstances, but aren't kind of forced on us by the kinematics. So the idea of lifting the superselection rule and of moving a constant of nature to a constant of motion, or no longer treating it as a constant of nature at least, I haven't said anything about motion, is then linked to the idea of epistemic perspective. That from a limited epistemic perspective, where we don't have access or manipulable control to all degrees of freedom, the superselection rules that we find, we don't really know whether they're hard or soft. And one can imagine moving to a kind of more enriched perspective where we have access to different scales, which could be numerical scale, could be energy scale, time scale, at which we understand that what was previously thought to be a hard superselection rule to be a soft superselection rule, which fits with the kind of general message of Poincaré's original example. And so this is the slightly pretentiously named principle. So just as the Copernican principle is about how our kind of position and viewing the universe isn't special, the idea is that our position and kind of understanding the scales that we have access to isn't special. There's nothing special about the scales which we currently have knowledge of. Categorization of constants as constant of nature, constant of motion, or as of superselection rules as hard as soft, is open to revision based upon kind of widening our epistemic window. How much time have I been speaking for?
So you have about 25 minutes, right?
I will speed up. So that's the first challenge, right? And I'm not saying this is a knockout argument that we have to do this, but it's create conceptual space and motivation for the idea of changing, reclassifying constants. So let's go to the thing that I was happier about, the formal motivation. And I'll try not to dwell on it too much, but happy to talk about more in Q&A. And so just to go back to the particle example, one of the best arguments that people give for the Dirac-DeWitt view comes from quantization of the relativistic particle. Because the kind of Wheeler-DeWitt type equation for the relativistic particle really is just the Klein-Gordon equation. So you get this mass shell constraint, and this seems like a quite sensible recovery of a relativistic quantum equation from the quantization of a classical relativistic equation. And moreover, it's kind of taken to be motivated by the classical gauge symmetry of the classical gauge symmetry of the relativistic particle, which is basically the fact we can reparameterize the trajectories. And this is essentially Hamiltonian, so it's really just saying that the idea is that Hamiltonian generates time reparameterizations. This is a very intuitive picture, lots of people have it quite clearly. This is also a superselection rule in the sense that we end up with superselection sectors kind of labeled as these kind of m squared, c squared eigenvalues. And what's interesting, and like I said, I essentially was reading about this today, so it's very new to me as well. Fock's paper is untranslated in Russian, and Stuckelberg's paper is untranslated in French. And so there aren't, I mean, there's some things knocking about online, but there's no official translations into English of either of them from what I can see. So you have to bear with me a bit.
Is that the tachyon paper of Stuckelberg?
I think one of them might be. I don't know yet. That's the next step. I looked at I found a translation of the Fock, and I've been through that. Sean reads French, so that's the draft I'm working on has a Sean to read French version note. Sean, if you're watching, that's homework for you. So I don't know. And so they basically give a proposal which is really similar to the kind of Poincaré and Giulini type move, where you reclassify the constant as constant of motion, you lift the constraint, and you end up with kind of with a different theory in general that you can recover by taking a special case where you fix a constant to 0. And the obvious response is, well, okay, but like, have you not done something bad with the symmetry? Most people, I think, would just treat this as a way of expanding the symmetry, expanding the representation space and gauge fixing to get back what you started with. But if you've gauge fixed the symmetry, then in some sense you haven't really preserved the structure of the symmetry. So it seemed to be, as much as this may be something you can do consistently, it's not seen to be something that shows that doing this is somehow consistent with reparametrization of variables. So it's, I mean, this is an argument people have made to me lots of times. In the end, the kind of details of responding to it is more detail I'll be able to go into this talk, but I'll just run you through the basic ideas now very quickly. And so the basic idea is just to start for what is a constrained Hamiltonian theory. Luckily, Clara has been giving talks, explaining to everyone in wonderful detail. But really, if you think about a phase space and you have a sub manifold within that space, phase space is a constraint manifold, and what you find generically is that equations of motion are underdetermined along something called gauge orbits. And what that means is that you can essentially move along these orbits without changing the kind of physical state. Dirac has a theorem which shows that motion along the gauge orbits is in a kind of precise sense doesn't change the state. So the natural thing to do is identify points along the state. It's an orbit of equivalence, an equivalence class, and then project out that direction. And that's where this procedure of symplectic reduction comes in. The symplectic reduction is the quotient of the gauge orbit of the manifold in which they live by the kind of constraints, and by the action of the constraints. And you can then project down to this reduced phase space where the differences between the kind of equivalence class have been removed. And I mean, unlike some people, like Brian Pitts, I'm totally fine with this picture in all other constraints apart from the Hamiltonian constraints. So I'm not going to be disputing it in the cases that Clara's written all these papers about, I think. Although you have written a problem of time paper as well, so maybe we do disagree. But definitely in the case of other constraints, I'm fully on board with the reduced symplectic reduction picture, which you don't have to be, but I think there's good reasons to be. And what's interesting is that I drew this diagram in my first ever talk. Shows you how much I've progressed. So there's a kind of nice way that you can match what we're doing with symplectic reduction to what happens in the quantum theory. And so people often describe this diagram as quantization commutes with reduction. And so the idea is if I have a constrained Hamiltonian theory, I can do this reduction theory step classically, then quantize, or I can quantize and then do the quantum version of the reduction step. And that's precisely what imposing the constraints as operators annihilating the wave function, the Wheeler-DeWitt type equation is supposed to do. And the idea is that in a precise sense, what these are just kind of boring superselection rule that just kind of pushes you down into one subsector, enforces the vanishing of the constant of nature. It's a hard superselection. And so if what was going on in reparameterization and variance matches this, there's a sense in which we've kind of messed up the entire structure of gauge theory. And there's something very confusing going on if that's true. So I wrote a book about this, at least about the classical problem. It was supposed to be about the whole problem, but we haven't quite got there yet. A lot of the stuff I was talking about is slated to go into the second volume, which will hopefully be finished at some point. And really the kind of long and short of what we do in the book is just contained on this slide and the table I'll do next. If you just restrict to finite dimensional systems, the time reparameterization invariant, which includes the relativistic particle and these cosmological toy models, but also things like Albertotti theory. Sean's basically created a geometric formalism that generalizes work by Woodhouse, and that allows you to kind of use a kind of first-order velocity phase-space formalism to write out the specific action of global time parameterization invariance. You can then isolate what is the underdetermination in reparameterization invariance. And it's basically, and this is something that Julian Barber said a long, long time ago, it's the scale of the velocity that's underdetermined. You don't get, there's no capacity for this kind of underdetermination where you get kind of paths that are kind of underdetermined in terms of their image, right? It's the scale of the velocity along the path that's underdetermined. And then you can explicitly demonstrate that reparameterization invariance is not a gauge symmetry in the precise sense that it doesn't correspond to initial value constraint, which is essentially the reason why we don't have the problem of initial underdetermination. And so Dirac's theorem doesn't hold. I don't think Dirac ever thought it did, but people seem to have assumed that. The way he sets it up, it's very clear that he knows it's not applicable to this case. Noah's second theorem is actually trivial for this case. They're called the Weierstrass identity is actually derived before Noether. It's one of the examples she uses earlier on. Whereas in gauge theories, they're usually non-trivial. In this case, they're trivial. There are no, you can pick out the orientation given by the reps as being tangential to the solutions, sorry, transverse to the solutions, whereas the gauge symmetry, they're tangential, and that kind of explains this. There's no initial value constraints, as already said, and this is exactly what you do implicitly is reinterpret the constant nature. And so the kind of picture that Sean and I did is kind of arguing this way. What I'm doing in the talk is trying to argue that. How am I doing for time now, Jenny? 10 minutes?
You have about 15 minutes.
Oh, that's fine. I'll even take it. Because I'm not doing the fourth challenge, so. I'll say some very sketchy things, but I won't actually try and solve it. So, research programs. We're doing toy models of quantum cosmology, right? And associated other things that are interesting, I guess, but progress is probably not going to come from, like, I don't know, bending of light ray Edison type experiments, right? We're a long way from that. There's some possibility down the line that you can start getting interesting results related to inflation out of these kind of paradigms. It's not clear if those are going to be testable, but so it's not that there's nothing that's possible empirically. I think there's plausible ways that you can get inflationary phenomenology out of this kind of stuff. There's a lot of exciting connections between these novel approaches to quantum cosmology and dynamical lambda, which I haven't looked into. João Magejo has some papers on that, look really promising. But I think for the time being, there isn't strong empirical evidence. There certainly isn't decisive empirical evidence. Plausibly at the moment, there's no empirical evidence. And as I said, because the alternative approach has the Wheeler-DeWitt approach as a special case, it's not clear that you could get decisive formal evidence one way or the other. But I think we can look at things that have been done and see that there's some promise to the research program. I was a bit probably more bullish when I was writing the slide. More progressive, both programs, I guess, can be seen as progressive. But I think there's some interesting results you can get from one you can't get from the other. And that's why I want to talk to you about the last 10 minutes or so. And I'll just do a high-level summary of this, because I have been through it before. Actually here, I think. The last time I was here, I think I gave a talk that turned into this paper, I guess, a while ago. So Sean and I wrote some papers, 2017, 2018, essentially applying this program to toy models of cosmology, and in particular the problem of singularities. And the nice thing is that what one can do is take a kind of simple Friedmann cosmology, it's homogeneous isotropic, just use a massless scalar field because you want to keep life simple, but then get rid of the spatial curvature as well, which is not so unrealistic, but keep the cosmological constant, and that's crucial. So we end up with this toy model, and with a bit of cleverness, you can write it in a quite simple Hamiltonian. And I mean, if you kind of squint, it's almost the harmonic oscillator, right? Because this is a memento, right? It's almost a harmonic oscillator, almost. So it's kind of a simple finite dimensional model.
It's like a damped harmonic oscillator? Is that like a
No, this one doesn't have damping. You can there's a version of this that's also damped. This is a symplectic system. What you find is that even this simple model has singularities in both the relevant senses. That generic solutions reach the kind of origin, A equals 0. V here is just the volume of the universe, right? Sorry, I should have said that. V is the volume of the universe, phi is a scalar field, pi v is the momenta of the volume of the universe, and pi phi is the momenta of the scalar field. And you find the generic solutions reach the 0 volume in finite proper time, and you can show they're inextendable. And you can also show that so you have geodesic incompleteness, but you can also show that there's a curvature blow up. So you've got a kind of toy model of a general relativistic space-time that's pathological in the relevant sense, and we can see if this is fixed by various quantization schemes. And whilst it is true that on these models in the loop quantum, in the Dirac-DeWitt approach, if you use the loop variables, you can avoid the singularity. You do that because of the loop variables. If you don't move to Ashtekar variables, you can show, in fact Ashtekar shows that in the paper I cited, that the model is singular in at least a kind of in the salient sense. I've written a whole paper about understanding what it is to be a singular model in quantum cosmology. See that if you want to know more. Roughly, it's the expectation values blow up, but there's more you can say about it. And in terms of fruitfulness, the central claim is that if you adopt this alternative approach, you can actually rigorously demonstrate that the model is singularity free. And to do this, you have to do quite a lot of work. You have to change variables because you don't have a well-defined momentum operator in the original variables. You then can construct a Hamiltonian operator, which, if you impose certain boundary conditions, you can show is self-adjoint, and you can then show that you get unitary evolution, quantum bounce, finite expectation values, all the things you would want of a kind of well-behaved quantum cosmological model. But this crucially really depends upon having cosmological constant and allowing for there being superpositions of cosmological constants and then the kind of general solution. So you end up with these kind of nice bouncing models. We're working on an extension of this, where the wave function is semi-classical at some early time, inverted commas. There's an hour of time in this picture at the moment, so take that under advisement. You get some semi-classical state. You evolve it backwards in time towards the singularity. You have some kind of bounce where the wave function kind of pushes into the singularity, it gets a bit messy, and it bounces back up, back out, and becomes semi-classical. And without introducing matter that violates kind of classical energy conditions, or introducing, at least there's no violation of the energy conditions in the semi-classical regime. There probably will be in the deep quantum regime. Or introducing kind of fundamental discreteness, which is not perhaps surprising that it removes the singularity. You can get this kind of ameliorative approach where you actually remove some of the pathology of the classical theory, which is great. What else can you do? I said progressive, not just like one thing. So very happily, Sean and I, since we haven't worked on this stuff for a while, some really wonderful physicists, I think both originally in Sheffield, although I think Lucia Mendes-Pidal has moved to Madrid, at least when I took this screenshot. So Stefan Gillen and Lucia Mendes-Pidal have written a series of papers, cited some of them earlier, I think, looking at some of the cosmological context, but they've just extended this last year to black holes. And so what you can do is basically run the similar argument in the case of the black hole and get not just singularity resolution, but some pretty interesting phenomenology or interesting kind of physics that is not expected. And I'll just kind of summarize this very briefly and then I'll end. So the trick really relies on this really clever idea that if you go inside the black hole, your space-like and time-like flip, and if you choose a very particular form of black hole metric, you can actually write the interior black hole metric such that it's the same as a cosmology metric, which I thought was really awesome. So there's something called a planar ADS black hole. Planar because the horizon is now R2. ADS because we're going to use a negative cosmological constant. You can show that this is has a horizon, which is this plane, but it also has a singularity in the relevant sense, which is actually a anisotropic singularity, so it's like a kind of stretching singularity. If you take this black hole metric, you can then, because of this thing about the interior metric, space-like becoming the time-like, even though it's exterior, it's a static space-time, in the interior, you basically have what's structurally the same as a non-static cosmological space-time. And then you actually end up being able to use the work we've done before to redo the same model. Because the Hamiltonian is the same as the one, in this kind of rewritten way, ends up being the same as the Hamiltonian here. And so you can use the same approach. You allow for this kind of lifted constraint, you allow for superpositions of cosmological constant. And this time, whereas before we focused on the positive cosmological constant and the bouncing solutions, here you focus on the negative cosmological constant, and you get this kind of, I'm still not entirely sure how to interpret it, a unitary bounce where you get a cycle between black hole and white hole spacetimes that are superimposed together. And there's various claims in the paper that how this might relate to some of the problems in black hole physics. This isn't an evaporating spacetime, right? So you're getting, it's a very different type of black hole white hole transition than the ones that people study in the context of kind of black holes shrinking and then turning into white holes. So, last challenge, how long have I got left?
You still have like about 5 minutes.
Okay, so I mean, so this is I don't want to diminish this. This is the most serious challenge to this alternative program. On the other hand, I'm not fully convinced that the Wheeler-DeWitt approach is actually dealing with this problem that well either, at least in the specific sense that it's not clear to me how faithfully the Wheeler-DeWitt program represents our ability to locally refoliate space-time in the quantum version either. In any case, the specific proposal seems to be quite wedded, that we're talking about seems to be quite wedded to having kind of a single global constraint or a single global constant that you promote to a constant of motion. And that's also the fact that we've got T here really does work on the basis of picking out a hypersurface, right? And so that's fine in the context where you've got a FLRW metric where all you have is a kind of sequence of hypersurfaces, right? You don't have any local structure, it's a homogeneous model. But once you start introducing inhomogeneities, it's unclear how to generalize these models. It is kind of, I think, just a technical problem to generalize the models to anisotropies, but generalizing them to inhomogeneities is not obvious. And this is something that people have done in modern cosmology called mini superspaces. So what to say about that? I think there's two different things that one could say. The first one, which is the kind of old line that we used to sell, which I think is still interesting, is that if you rewrite generativity in terms of shape dynamics, then you've kind of removed that problem by changing your refoliation symmetry to volume-preserving spatial conformal transformations. And so maybe you can just say, well, we're going to use a formalism which has a fixed kind of global mode of the Hamiltonian, but then we have different local symmetry. The alternative, which I'm interested in pursuing at the moment, is based on something called the BKL conjecture, which is that closer to the singularity, the universe becomes like effectively a series of little anisotropic toy models, like Bianchi models. And so the idea is that if we can show that it's all about singularity resolution, if we can show in the regime where the universe is effectively described by these coupled, or with these kind of like kind of localized Bianchi models, then we've got singularity resolution, even though we haven't quantized the full homogeneous sector, because we know in the limit, when we get close to singularity will be avoided because we can use these models. So that's something, the argument we're working on at the moment. I think there's still more to do, but it's kind of, in a Lakatoshian sense, there's reason to believe in it as a research program. Thank you very much.